Hello, this is a lesson on section 11.2 from your Algebra and Text. What we're doing here is we're graphing basic square root functions. And it's a close relative to what we just talked about with quadratic graphs, y equals x squared. What we see with the quadratic graph is a parabola that opens up with a vertex at 0, 0. And the thing about a square root graph is that it's actually a sideways parabola. The sideways parabola, but it's only half of it. So it's the exact same curve as what we see here, but it's just half of it turned sideways. What we want to do is we want to look at how does the basic square root of x graph look like and how can we change it with parameters. What we're going to do is we're going to plug in values of x into the square root of x. Let's see, you might notice here that the square root of -2 is not real. So it turns out that there is no number that when you square root it is, the square root of -2. The same thing happens with -1, and so the square root of 0 is 0, the square root of 1 is 1, and the square root of 2 is approximately 1.4. I'm going to add another number to the input. Let's use 9. The square root of 9 is equal to 3. So if I plot these four ordered pairs, 0, 0, 1, 1, 2, 1.4, and then 9, 3, I will get a graph that looks like a sideways parabola, but it's only half of it. So what we're going to do next is what happens if we multiply the front of the square root of x by 3. Well, remember, -2 and -1 are not in the domain, but if I plug 0 into x and then multiply by 3, I'll get 0. Plug 1 into x, multiply by 3, I'll get 1. And then 3 times the square root of 2 is 3 times 1.4, which is 4.2. And let's do that other one, 9. 3 times the square root of 9 is 3 times 3, which is also 9. So graphing these ordered pairs, we can see how this relates to the square root of x. So we have 0, 0, we have 1, 3, 2, 4.2, and then at 9, the y value is 9 as well. So here's the graph of 3 square root of x, and what I have for the red one is the square root of x. So what you see here is a vertical shift. As the value of a is a whole number, the graph will stretch, we would say it stretches vertically. Let's look at another parameter change. Another one would be if we have a negative in front. So for this example, let's change it to negative square root of x and talk about the half later. So the negative square root of x is what we might call it a, all right, so I fixed the screen. If we have negative square root of x, we might say it's a reflection over the x-axis. And what we're going to do here is we're going to go ahead and plug our domain into the function. Let's see, the square root of 0, but the opposite is just 0. This is the opposite of the square root of 1, which is 1. And the opposite of the square root of 2, which is negative 1.4. And then plotting these points, what you see is the square root graph, but it's a reflection of it across the x-axis. So it looks like that. And compared to, let's go ahead and write that down. So that's negative square root of x. And then if I put the square root of x here, what I would say is that these are reflections of each other across the x-axis, which is the line of symmetry. So here's another parameter change. If I add 2, so once again, we're going to look at adding 2 to the function. I cannot plug in the x values that are negative here, but I can plug in 0 to get 0 plus 2, which is 2. I can plug in 1. Let's see, the square root of 1 plus 2 is 3. And then the square root of 2 plus 2 is equal to 1.4. 1.4 plus 2, which is 3.4. And let's go ahead and plug in 9 to get another point. So that's the square root of 9 plus 2, which is 5. So I have 4 ordered pairs. I can plot 0, 2. I can plot 1, 3. I can plot 2, 3.4. And then my fourth point is 9, 5. So 9, 5 is here. So what I see is an x squared graph, but it's shifted up 2 units. So let's compare that to its parent function. This is x squared, square root of x plus 2. And if I sketch the parent function, the square root of x, I see it's a vertical shift up 2. And so our generalization here is adding and subtracting a k to the outside will shift the graph up and down. The final transformation is shifting it left and right. Down here at the bottom, you can see that if I add or subtract a number on the inside of the square root, we're going to shift it sideways. So let's just look at our table values here. I'm starting with 4. The square root of 4 minus 4 is 0. The square root of 5 minus 4 is the square root of 1, which is 1. Let's plug in 8. So I would square root 8 minus 4, which is going to be the square root of 4, which is 2. So if I graph these 3 ordered pairs, 4, 0, 5, 1, and then 8, 2, I get a square root graph, and let's compare that to its parent function. The parent function is the square root of x, which looks like this. And what we see here is a sideways shift. But notice it's counterintuitive. If we take away 4, if we subtract 4, we're actually going to shift it to the right 4 units. But if we would have added 4, we would have shifted it left. So that's summed up down here. So make sure we note that. So one thing we could say is that we now have a square root function with 3 parameter changes. And we can write this in a one function notation where we have A is going to be, if it's a reflection, and it also affects, it's a vertical stretch. Okay, and then let's see, if we have an H, we would do a horizontal stretch, excuse me, horizontal shift. And then if we add a k value to the outside, this is a vertical shift. So this is a great illustration of those H, K, and A values. With this illustration, let's first look at the A value. As we decrease the A value, you'll note that as A increases, it's a vertical shift, excuse me, a vertical stretch. And as A becomes negative, it's a vertical stretch, but it's also a reflection across the x-axis. That horizontal shift, if I have a negative H value, x minus 4, what we see here is that it shifts it to the right 4 units. But if I have an x plus 4, it shifts it to the left. So it's the opposite shift that you might think. With a vertical shift, it's exactly what we think. As k increases, the graph shifts up. So with a positive 4, I shift up 4 units, and then with a negative 4, it shifts down 4 units. So the final thing we need to talk about is how do we find the domain of these square root functions? So to find the domain, what we do is we set the inside of the square root, greater than or equal to 0. So let me try to illustrate that with, suppose we have y equals the square root of x minus 6. The domain of this function is going to be all positive values greater than 0. All right, so what I did is I took the inside of the square root and I set it greater than 0, and we can make sense of this. If we were to plug in negative values into the square root, it wouldn't produce anything that's a real number. We can't square root a negative. So let's look at a different example with a different domain. If I add a horizontal shift, y equals the square root of x minus 4, this will change the domain. So what I'm going to do is identify the expression inside the square root, and I'll write x minus 4 must be positive or equal to 0. So this is the domain. We can clean this up and say that the domain are going to be all x values that are, let's see, I can add a 4 to both sides, that are greater than or equal to 4. Okay? So another example that we might look at to illustrate this is suppose I have one where all the parameter changes are being used. Notice here I have I have a square root graph, but the only thing I worry about when figuring out the domain is going to be the inside expression. So the domain is going to be all numbers x minus 4 that are positive. So x must be greater than or equal to 4.